Yes, good afternoon.
Good afternoon, sir.
Yeah, where was it stopped? We had started, no, this?
Yes, sir.
This one? Was it done till here?
No, sir.
No, this is not done. Okay.
Slide 3 was done.
Okay. Okay. We started this writing and optimizing the ARM assembly code. So in the previous sessions, we understood how to write the ARM assembly code. So now what we are going to learn is how to optimize the ARM assembly code. Uh, so code optimization brings you a lot of advantages. One is it reduces the system power consumption and also reduces the clock speed needed for the real-time operation, and also makes your infeasible system into a feasible one, and then converts an uncompetitive system into a competitive one. So, and also provides you the maximum performance. Okay, and writing assembly code always gives you a lot of performance. So why? Because it has three direct control of three optimization tools. Now, what are they? Instruction scheduling, register allocation, and conditional execution. So these are the three optimization tools for which the assembly code has the direct control, and hence it provides you the maximum performance. And now register allocation. So again, you can decide among the 16 visible ARM registers which one to use. Okay, and there are two other registers, stack pointer and program counter. And whenever you're using the thumb code, okay, and if you want to call a procedure, so there is a certain standard which you need to follow that is called as ATPCS standard. Okay, and according to this standard, what it says is in the thumb code, whenever you're using the registers R4 to R11, they got to be preserved. So it is necessary for you to save the registers from R4 to R11. And again, another standard, this ATPS PCS standard, what it says is, it also says that the stack should be aligned, 8-byte aligned. That means whenever you're pushing something onto the stack, it has to be stored at an address which is multiple of 8. So, and again, by doing this, you can go for increasing the performance of the system. Next, writing an assembly code. Now, what I've shown here is a C code. Okay, main.c is the program name given, and what the C code is doing, it's basically finding the squares of the number from 0 to 9. So 0 square it prints, 1 square it prints, 2, 3, 4, 5, 6, 7, 8, 9. Till 9, it goes for printing the squares of the number. So this is the normal and very simple C program, what we have written for that. Now we understand how to convert this C code. So this everything was in thing. So main function and then square is also there. So the function square is also written over here. So if I go for executing this, fine. So the square function is called and it returns I into I and it gets printed. Now what we are trying to do here is, see, I have written something like this. So main1.c is my C program, and what I've written here is only the main function, and the definition of the square I'm not writing here. Okay, definition of the function square is not present. Now where I'm writing the definition of the square, so definition of the square I'm writing here in the assembly code. So this I'm giving the name as main1.c, and for this I'm giving the name as square.s. So in square.s I'm writing the definition of the square. Okay, so just observe here, this is area text. See, whenever you're naming the area, if you're using a non-textual character or non-alphanumeric character, so then you got to enclose them inside the vertical bars or the vertical lines. So I have used a non-textual non-alphanumeric character dot here. Whenever you, even you can go for using non-alphanumeric character for naming the area, whether the data area or the code area. So if you're using any such non-alphanumeric character, then it has to be enclosed inside the vertical bars. And you can observe here one more assembler directive with the name export. Now export and square I'm writing because now I want my main 1.c whenever it calls a square, so it is this function that gets called. Okay, that means so I'm telling my square.s that this square function it can be called by another programs, and who calls this right now? So the program which is written in C. Okay, so this talk you can make a program which is written in C talk to what the square.s which is written in assembly code. Okay, so if you want to make this square function which you're writing here, the definition which you're writing in assembly code to be accessible by another program, then you have to use export square. Okay, and you got to use the same name. Export square I've written, and in the other programs you got to use the same name, square. Okay. So export square, and this is what the definition I'm writing. Okay, I said so I'm calling the square from here, and I am passing. I is the argument that is passed. Now how this is going to receive it? So always whenever passing only one argument, it always comes to the register R0. Remember that. So if you're passing one argument, see I'm calling the square method by passing one argument. So it gets copied to what register? Always to register R0. I have my number, correct? No, the argument which is passed now in the register R0, it is R0 into R0. Okay, I get the result in R1. Okay, and again I'm putting the result which is there in R1 to R0. Why? Because again the register R0 is used for returning the value. Now this has to return, right? So this function square should return the value here, and this will go for printing the value. Now how do I make the square return the value? Again it should be there in the register R0. Then put the address which is there in LR register back to PC, because this function from where it is called from here. Okay, and after that, after this function is executed and the result is stored in the register R0, so again you need to put back the address which is there inside the link register to PC. Okay, so this is which we have already understood, because LR holds the address of the next statement. From here you're calling the square, LR holds the address of the next statement. So, and putting that back to PC will make, after calling the square and printing, again it will make the function go with the next iteration of the for loop, and again it calls, and the process is going to repeat. Okay, now so now you understood now many things here. See, so you're calling the square function which is defined inside the square.s, and here whenever you want to use an alphanumeric character in the area name, so you got to enclose them inside the vertical bars. Whenever you want to make this particular function, square function, invoke from the another program, then you got to make use of the assembler directive export. Okay, now so any doubts in this?
No, sir.
Okay. See, this is very interesting. Try to focus and understand. And this is what is the return statement. Okay, so putting the address which is there in the link register to PC is nothing but the return statement. Okay, now whenever the square is called, address of the next statement, that is the next iteration of the for loop, gets loaded into the LR, and then control comes here. Once the square is found and it is put into the register R0, so we are putting back the value which is there in LR to PC. Now the control comes back here. Not only the control, also the value which is stored in the register R0 is returned. Okay, now here few things are written. So the area directive names the area, and this is the area dot text. And if you are using a non-alphanumeric character, so in the name of the area, so then you got to enclose them inside the vertical bars. Okay, next. Okay, this is what an export directive. What export directive is doing? This export directive, it makes the symbol square available for external linking. That means, so this it is possible if I this square function is made externally possible to link. Okay, and how to compile and how to make it link, all those things I'll show you. So at line 6, we define the symbol square. This is the square as the code label. That means whenever any program calls the square, it starts executing from here. Okay, next. So all this is fine. So return the control back. So this is how we do it. So move PC comma LRV right. Now when this statement gets executed, it also returns the value which is there in R0. Remember this. Okay. And end assembler directive you already know. Let me skip this. And yeah. So the first argument, whenever you pass an argument, so as already mentioned, one single argument, it gets copied to R0. So what if you're passing two arguments, say I comma j, square I comma j, one more argument of passing. So the first argument I gets loaded into the register R0, the second argument j gets loaded into the next register. What is the next register? R1, something like this. I have examples on those things also. We'll learn them later. Now, okay, done. Now I've written separate programs now. Main.c I've written like this. Square.s I've written like this. Okay. Now what I have to do? So I have to make my execute these two. Okay, and make my main1.c call the square function which is written here. How to do that? So we got to do like this. So building this example using the command line tools. So we have something called as ARM CC. So you cannot do anything on the key IDE now, where we were executing the program earlier. Now what I'm doing, using ARM C compiler, okay, I'm compiling my main1.c. Now when I compile, when main1.c successfully compiles without any error, so I get this main1.o.obj file. I guess all of you know this object code. Okay. So main1.o is the object file that is generated. And after that, I'm assembling ARM ASM, assembling my square.s. Now, once the square.s is successfully assembled, I get the file square.o, that is the square.object file. Now I got to link these two. How do I link? Using ARM link. And -o is the option again. And this is what the output file I'm generating. You can give any name. So, but I'm taking the name as main1 itself. Okay, main1.axf ARM executable file it is. Now what it will do, ARM link, it will link these two. So if you don't link these two using ARM link, so your main1.c cannot call the function square, which is defined inside square.s. Okay, you got to link these two object codes. How? By using ARM link. Now these two got linked, and there is a new output file that is generated. What it is? Main1.axf. That is ARM executable file. Now if you execute this, so if you run this, then what it will do? It makes a call to this square function which is defined inside square.object code, and all the 0 to 9 square it displays. Okay, but the squares are being found by or computed by your square.o. Hope people are able to understand.
Yes, sir. Yes.
Okay, now we'll do this. Okay, we're going to do this. We're going to compile using ARM CC. We are going to assemble using ARM ASM, and we are going to link them by using ARM link. I'll show you how to do all these things. So let me show you where are all those ARM C compiler, ARM ASM, and ARM link. So they are here. So if you have, just go to the directory where you've installed Keel. See, I've installed Keel to my C drive. I'm just opening C drive. And there is a folder with the name ARM. Open this. And again, inside ARM, there is something called as ARM CC. Open this. Okay, and inside ARM CC, there is something called as bin. Open this. Okay, you can just see now. See, ARM ASM is here. It is an exe file. Okay, let me show you. Go to the properties. See, it is an exe file, .exe file, executable file. So it is an exe file. ARM CC is another exe file. ARM link is another exe file. And these are the three things which we are going to use now. Programs I already have. See, main1.c. Main1.c. I've already created it. So I'm not going to create them again. So let me delete this main1.afx because I want to show you that it gets created when you do ARM link. Okay, let me delete that. And then main1.o also I'll create, delete. So main4, this was for the another program. Let me delete that as well. So main4.o, this also I'm deleting. Square.o, I'm deleting this. This is square.s file. Okay, this is our ASM program. Okay, and this also let me square. Okay, and then sum of let it be there. Okay, all these things let it be there. Now I'm opening your main1.c. So this is what the main 1.c, the program which I showed you in the PPT. This program main 1.c, this is the program. It's the same thing. So I don't have the definition. I have only the main method here. See, main, only the main function, and the square definition I've not written here. And then the other one is square.s. I'm opening it. See, this is square.s, where we are finding, see, export square, and this is what I'm finding. Then put, so now whenever this main.c, main1.c calls the square, this I value gets copied to what? First register, that is R0. R0 into R0, result goes to here. And why we are taking it back again to R0? Because the return value should be there in R0, because this will return now. Then put LR to PC register end. Okay, so these are the two programs what I have now. Okay, so now my main will talk to main.c will talk to square.s. Okay, now what we will do? So I got to compile first my main program using ARM. This is, since it is a C program, I got to compile it using ARM C compiler with -c option. And then I have to translate my square.s using ARM ASM. Okay, and then using ARM link, I should go for linking the object code obtained after compiling this and object code obtained after compiling this. So with some output file name. Okay, now let us go to the command prompt. I guess you people are able to understand.
Yes, sir.
Okay, I'm going to the command prompt now. Yeah, so I have anaconda.prompt also, but normal command prompt is required for us. I'm going to the command prompt. So this is the command window. What I'll do now, so I just go to this directory, C drive, keel, ARM, ARMCC, and then bin. Right now in Arish BT. So let me come back. I'm in C drive. Okay. Now I'll go to, so in C drive, I need to enter into the folder called keel. I guess you people know how to do that. You got to use the command cd to KEIL, keel. So I'm inside the keel right now. You can see C drive, I'm inside the keel. So CD to ARM next. So I'm inside ARM. I've come here now. Now I need to go here, ARMCC, CD to ARMCC, and then CD to bin. Okay. Now my command prompt is right now here. It is locating here. If I put dir, so you can see all the files which are here. See ARM, AR. So along with all these files, there are two other files, dot and double dot. So next semester you'll understand when you study Unix system programming. So there you'll understand what is dot. Dot is a present working directory and double dot is its parent directory. These are the two default files which are created. Whenever a directory is created, these two default files are created, and these two are hidden files, so you cannot see them. Only when you do dir you can see them, dot and double dot. Okay, all that is not required for us. You can see all the files here. So main1.c, main4.c, square.s. Okay. Now let me go for compiling. So all of you can see my command window, right?
Yes, sir.
Okay. Now I'm compiling my C program, ARM CC. So -c is the option, and my C program is main1.c, which has only the main function, but the definition of the square is not there. I'm compiling it. See, it got compiled successfully. So it's saying me one warning. So one warning and 0 errors. Okay, no problem. Warnings can be ignored. What a warning it is saying is, so square function is not there, right? So I'm not given the definition of the square. So you can ignore, no problem. Okay. So warnings can be ignored. So now we'll assemble ARM ASM. What is my assembly code? It is square dot, yes, it's a S file. Okay. Square dot, yes. So my assembly. No, and before that, so I forgot to show you that. So after compiling my main1.c, see, is there a main1.o generated? See here. Can you people see this?
Yes, sir.
It's the object code that is generated and the machine code. And similarly, after I successfully compile my square.s, see, for square.s there is square.o generated. Got it?
Yes, sir.
Okay. Now using ARM, ARM link. Okay, and while linking, the output file will generate now. Now for this output file, you got to give some name. So any name. So this -o you have to use. So that means by writing -o, I'm telling generate an output file. So minus is nothing but hyphen it is -o. So generate an output file with the name main1, because my C program name is main1. Okay, dot axf ARM executable file. So right now you cannot see that program, that is not there, that file is not there. Now how do I want this main1.axf to be generated? By linking what and what, main1.object file and square.object file. Now what ARM link will do now, it will link these two now, and then it generates the output file main1.axf. Now if I go for executing this, so now your C program, this main1.o square, it calls and it goes to this, and this finds the square and returns back the value to this. Okay, so now the output file is generated. You can see now, see main1.axf is generated. So it's an ARM executable file, so AXF file. So you cannot open this. So even if you try to open this in the Notepad, okay, Notepad++ I'm trying to open. So it is all machine code, you cannot understand. So who can understand this? Only the CPU can understand this. Okay, not us. So it is not in the human readable format. So this is what is generated. So I don't know whether people have noticed or not. Even our keel generates it when, say, let me open. Okay, now let me translate this. See, program 7.s, 0 errors and 0 warnings. Now when I build, see, even this also says program 7.axf is generated. So program 7.arm executable file. So all of you observing here?
Yes, sir.
So this is the .axf file generated, but this program is purely the assembly code, and we have not linked any C program to this. But by doing here, what we did to this assembly code, we have linked. This is the object code generated out of the C program, and this is the object code generated out of the assembly code, and these two are linked, and this is the output file generated, and this output file has both main.o and main1.o and square.o, and if I'm able to execute this, now it goes for printing the square. So now the thing is, so I got this main1.axf, so I don't know how to put this main1.ax, and now if I click on debug, what debugger will do, it will automatically take this program 7.axf, and then it starts executing. So, but I don't know. Now I have directly obtained this AXF file here. Where is that AXF file? It is in my C drive. It's in the bin directory. I don't know how to give this here directly to the keel ID for execution. I was just trying to find a method in order to directly take read AXF file and run. So, but I was not able to do it. So let me find out a mechanism how to do that, and I'll show you. I'll execute this and show you. Where is that? I'll execute this and show you. Okay, so right now execution I'm not doing, okay, because what I know is there is a special simulator for running AXF file. Okay, so one thing I need to search for that special simulator I have to run. Otherwise, I need to find a mechanism how the AXF file can be directly dumped here and can be debugged. Okay, let me find out the mechanism for that, and after that I'll show you. Now we'll continue our discussion. So I guess you people got an idea and understood.
Yes, sir.
Okay, so now it looks very beautiful now. So now you can make your C program talk to the assembly code. So high level code talking with the low level code. Okay. Okay, now this is what you understood. So calling the function square from C, which is written in square. Sir, is it possible to call a function which is written in C from the assembly code? Yes, that is also possible. Okay, that is also possible. You'll see that also. So what we do from our assembly code, okay, from the assembly code, we call the printf statement. So where is what is printf? Printf is a library call, C library call. Now, is it possible to call the printf C library call from our assembly code? Yes, it is possible. I'll show you how to do that. Okay, this is we finished. This also we finished, and we went through how to compile our C program, how to assemble our what square.s, and this square.s again you can do it directly here also. So just open square.s here, you assemble it, and you get what program 7, sorry, square.axf file. So directly you get square.axf file, but that square.fx is different. Okay, because it is without our C object code. So C object code should also be linked with that. So for that purpose, we are doing it at the command prompt. So now this ARM link is able to link both the things and generate a new executable file, that is main1.axf. So let me find out something must be there to load only the axf file. Okay, let me find out, because this is not the time to search. Let me find out. Let us continue. Now, okay, what we did here. So we compiled using ARMCC. When I use ARMCC, it compiles my main1.c to what? ARM code. Okay, so ARM code. Now, is it possible to compile your C code as thumb code? So thumb code, you know, what is a thumb code? What is a thumb code? Hello? Please unmute and talk. What is the length of the instruction in thumb code?
16 bit.
16 bits. Okay, it reduces to 16 bits. Now how to write? See, easy. That also you can do. So you write a normal ARM code, and this can be assembled and compiled into a thumb code. How? I'll show you. But one difference is that, so this is the same square2.s. So square.s, I've renamed it as square2.s, and only change is that here we had written it as move pc comma lr, but move pc comma lr will not work in the thumb code. Now instead of move pc comma lr, you got to write it as bxlr. So bx, I don't know whether you remember while discussing the branch instruction. So I told bl, branch and link, and there was bx and bxl. Now this is what bx you have to use. Okay, so bxlr. This is same as move pc comma lr. Okay, and it also returns r0. Okay, so this is what the code I'm writing. Now how do I compile it into? I don't want it as an ARM code now. So I want it to get compiled as a thumb code. Okay, so now instead of ARMCC, you got to make use of TCC, thumb code C compiler. So thumb code C compiler minus C main1.c. If I do, now the object code what I get, it is a thumb code. So all the instruction length is not 32-bit, it is only 16-bit. Hope people are able to understand.
Yes, sir.
Okay, now do I have this thumb code C compiler? No, I don't have that. So I need to search. So let me go where here. See ARMCC. So I am only the ARMC compiler. So I don't have this TCC. So I have ARMCC exe file, but TCC exe file is not there. So even if I go back, so come back one more step. So what I have is this ARMC compiler. The TCC I don't have. Okay, so you can find always. You can also get the TCC, but since I don't have that TCC, I'm not going to compile and show you this. Okay, but you understand it. And after that, even our square2.s, I need to compile it and generate the thumb code again. So you got to make use of this option minus APCS. Okay, so what is this APCS? So here I mentioned it. So this one ATPCS here, ARM thumb procedure call standard, because whenever you're compiling your assembly code to thumb code, okay, so you got to make it follow these standards. So that is the reason we are including this APCS slash interwork. Okay, and we also got to make this square2.s interwork with the main1.o object file that is generated. So same thing. These are the changes, and then ARM link is same, exactly same as what we understood in the previous slide. So main1.o square2.o. So these two are the thumb object codes right now. So we're linking them under the name main2.axf. And if you get a simulator, you can go for running this. Okay. So OP got it.
Yes, sir.
Okay. Next. Okay. So now till here, so we understood how to call a function from C whose definition is written in assembly code. Okay. Now opposite we are discussing. Calling a C subroutine from assembly code, calling a function which is written in C from the assembly code. Okay, so this is what you have to understand very carefully now. See now, so area, this is fine. All of you know this. Now instead of export, this is export main. Okay, and now when you want to use a function which is defined in C program here in assembly code, you got to make use of import. Okay, import. See, import, and say I need to import all C library functions. Okay, how do I do that? See, lib $request $ARM lib. So all C libraries are imported here. And what this week says is, so when it is importing all C library functions, so if for some reason, if any of the library is not found or it could not be imported, so then I don't want an error message to come. I just want to suppress the error message. Okay, if any library is not found, just suppress. Now for that purpose, you need to use weak. So if this assembler directive weak is not used, so when this assembly code is importing all the library calls, and if any of the library is missing, then what it will do, it will generate an error and it will not allow the further process to happen. So just to suppress that, so error messages I'm using weak. So whatever the library calls are available, let it import, and whichever is not available, let it not worry. Okay, that is what weak says. And then import _it is _main, that is the C library entry. You know, in a C program, always the execution starts from the main. So that is what I'm specifying. Then I want to use printf statement in my assembly code. Okay, now I need to call printf in my assembly code. So import printf. Okay, now rn4. Okay, 4 rn is the register number. So this is another assembler directive. 4 is the register number, R4. Okay, so in my assembly code, so I don't say whenever I want to use register R4, what is that I used to write? R4. No, I don't want to use R4. Instead of R4, say I need to use I. So I need to make, so what I'm doing now, I'm making I as an alias name to register R4. Hope people are able to understand. So henceforth, when I'm writing my assembly code, instead of R4, I can go for referring it by using I. Are you people able to understand?
Yes, sir.
Okay, next. Yeah, import is the directive used to declare the symbols that are defined in other files. Okay, printf is not here. Printf is a C library call. I need to bring that here. Now I need to make use of import. Okay, and before this, so this all libraries should be imported by writing this statement. And why weak specifier? So to prevent the error messages. If any of the library call is not found during the linking, it generates error. Just to suppress that error, we are writing it. Okay, all this is an RN directive. So importing printf allows us to call the C library function. So I've imported the printf here. Now I can call this printf and then I can go for printing something on the std out. Now RN directive allows us to define I as an alternate name for the register R4. So 4 I'm writing here. Now this I acts as an alternative name for the register R4. Now this is my program. See, everything I've written, the thing which I explained in the previous slide here. So the same thing is written over here. So look into the other part right now. So main I'm writing. Okay. So now even some other program can go for using this main which I'm writing. So I'm using the key assembler directory export and main is also written. Now see, observe now. So this you know very well. So store multiple full descending stack. So stack pointer and I am writing here. What does it mean now? What is this I? What is this I?
R4.
Register R4. Okay. Now, so this is my store, right? I'm taking the content from the register R4 till the LR and then storing into the memory location. So reading the content of all these things and storing them into the memory location in the form of full descending stack. Everything we have understood. And then move I comma 0. I'm storing initializing R4 register with 0. And then print string. Observe now ADR I told. So this is the instruction which we use to load a 32-bit relative address. Okay, say this is print string, which is a label. Now I want the address of this label, so I cannot use LDR. LDR can be used only to load the addresses of the memory location, but this is a label. Now I want this label address now in register R0. I'm using ADR. So print string. Okay, just observe this print string now. So print string, what I've defined in the memory is just observe square of percentage d is percentage d. This is what you write inside the printf statement. Now I've written here. Okay, observe now what I'm doing. So this is what I've written. So print string. Okay, now observe here. I'm putting the value which is there in I register R4 to R1. Now multiplying both the things I into I get the square in R2. Okay, in the register R2, then branch and link to printf. This is what I'm calling branch and link to printf. Now when I call this, so 3 things you got to notice here. Observe here. First thing is this R0. It will take R0. What is there in R0? Address of print string. That means so this is passed to printf. So I'm calling branch and link printf. So this is what is passed to printf. And so and it will take it from the register R0. R0 is holding the address of this string now. This so the whatever is stored in R0 from that address till it sees 0, everything is passed to printf. And now printf, I've written the placeholder percentage d. Where will this get the value? This gets the value from R1. The next register R1. And this is the placeholder for displaying the value which is there in the register R2. Hope people are able to understand.
Yes, sir.
Okay, see branch and link printf. Now what happens since I'm using BL, address of this statement add, it goes to which register? Let me take pen. Address of this statement goes to LR. LR gets the address of add. Address will say this is 1000. So this address goes to LR. And then PC. PC is set with the address of what? The printf statement. So printf. So now CPU is performing the execution of printf. And now for printf to execute, it requires data. What are the data? See, this is what I have prepared before calling printf. This is what the preparation I have done. So R0, it must be the address of the string that you need to display using the printf statement. Okay, so R0 is passed and R1 is passed and R2 is passed. Using R0 printf, understand this is what the string I need to display on the screen. And then while it is printing, yes, SQUARE space OF, it will print and then a space. And then it says, oh, there is a placeholder for displaying the integer. From where it will get the value? So from the next register, what is it? R1. Then space, E space. And again, there is a placeholder for displaying an integer. From where it will get the value? From the next register. What is that? R2. Okay, people are following?
Yes, sir.
Okay, now your assembly code is calling the printf statement and trying to print the square of 1. Say, for example, in R0, in R4, how much I have now? In R4, I have 0. 0 into 0, 0. Square of 0 is 0. And whenever you call it again, okay, so because you're going to read all the numbers which are there in the stack pointer, okay, whenever you read the next number 1, square of 1 is 1, square of 2 is 4, square of 3 is 9. It goes like this. And we are comparing. Compare 1 with 10. Okay, so what is the value? I. So this is not 1. Compare. So add increment I, because initially it was 0. Now increment I, how much it becomes? 1. Compare 1 with 10. So branch and less than to loop. Yes, 1 is less than 10. Go back to loop. Again, put the address of the print string in R0. Now 1 goes to R1. 1 into 1. So why we are storing 1 in R1? Because this is required for the percentage D here. Understood? So the first placeholder gets the value from the register R1. The next placeholder gets the value from the next register, that is R2. Say for example, I have one more placeholder, percentage D, one more I'm writing. Now from where it will get the value? From the next register, that is R3. Hope you people are able to understand. It is in this sequence. Okay. Now this is the complete program. Okay. So where your assembly code is calling the printf statement, C library call printf statement, and it is printing. This message gets printed on the where the standard output on your monitor. Okay. All these days we were seeing the output where? On the memory or in the register. So now just by writing this, you can have the square of percentage D is percentage D printed on your standard output, just like your C program used to print the output on the standard output, right? So same way you can do that. Is that clear?
Yes, sir.
I have another example now. So this example you'll understand still more. See again. So stdio.h main function I've written only main function, and the function sum of I'm not writing. And observe this sum of now. So sum of here I'm calling with only one argument 0, and here I'm calling with 2 arguments, and here I'm calling with 3 arguments. 3. See how many arguments are there? 2. So here only 0, and this first number is telling how many arguments are there. Okay, 1 argument. And this first number is telling how many arguments are there? 2 arguments, 1 and 2. And this is 3 arguments, 1, 2, 3. And this is 4. So first argument I have intentionally made it as the number of arguments. Okay, excluding this. Okay, 1, 2, 3, 4. And how many arguments are there here? 5. 1, 2. I need to find the sum of 1, 2, 3, 4, 5. Next, I need to find the sum of first 6 numbers. 6. Hope people are following.
Yes, sir.
Okay, now
Yes,
come
sir.
here. So this is the function. So the function which I am calling sum of is implemented, or definition is written inside the assembly code. This is what is my assembly code, and which is implementing the definition for sum of. Now I want my main.c to call the assembly code in which the sum of definition is written. Okay, now this is all of you know this. So what I'm doing, I'm making n as an alias name and an alternate name for the register R0, and similarly sum is the alternate name for the register 1. OP people are able to understand?
Yes, sir.
Okay, now here, see here. So let us say this sum of. Okay, this is the method. This is called. Where it comes, how many arguments we are passing? Only 1. Where it gets copied? To register R0. Now R0, I'm referring it by an alternate name called as n. So sub as n, that is R0 minus 1. Okay, 0. Now whenever this sum of is called, what is the value that is passed? What is the value which is there in R0 or n? N R0, both are same now. What is the value here? What is the value? What is that you're passing here?
0.
0. And it gets copied to which register? R0. R0 is nothing but what now?
0.
N. So N as 0. 0 minus 1. Okay. Or move less than. See, you're checking move instruction with the condition less than. Is N value less than 1? 0 less than 1? True or false? Please answer me. Is 0 less than 1?
Yes, sir.
Yes,
Yes,
true it is. Now what is that you're moving? Sum is equal to 0. Okay. So do we have one element? So no elements to sum. So if the function sum of which you're calling is with only one argument, so then that is 0. So then we don't have to sum. No elements to sum. Now what is the sum now? Sum is 0. So move this 0 to sum. That is move 0 to the register R1. So register R1 gets the value 0. Hope you understood.
Yes, sir.
Okay, next. So this is the function called sum of. What is the time? Okay, so sum of with two arguments 1, 1. Come here. Now register R0. Okay, gets filled in with the first value. How much it is? 1. Okay, and R1 takes the second value, that is 1. So this goes to R0, this goes to R1. Come here. Now here I have 1 now. 1 less than 1. Condition is false. Don't move this 0 to the sum. Come to this. Sub s 1 minus 1. Okay, 1 minus 1. And we have here had greater than or equal to. G is nothing but greater than or equal to. Now 1 is equal to 1. True. Now what is that you are adding? See, sum. Which register is this? Tell me the register.
R1.
R1. So R1 is holding what now? First number. Is it 1? Yes or no?
Yes, sir.
And what is R2 holding? Hello? Sorry, this is R1, right? So R0 is holding this first one and R1. So this R1, okay, so is holding the second one. So sum is 1. The current sum is 1 and this is 1. Okay, 1 plus 1. How much you get? 2. Okay. Next, take this next sum of with 3 parameters. So this goes to this 2 goes to R0. This 1 goes to R1. This one goes to R2. So remember, this is in R0, this is in R1, and this is in R2. R0 in our case it is what? N, and R1 is sum. Come here. So N is how much now? Number of elements. What goes to
2.
R0? 2. So 2 minus 1. 2 minus 1. How much it is?
1.
So 2 greater than or equal to, greater than or equal to. Now sum is equal to sum. So previous sum plus R3. Okay. So repeat this. So like this. So it starts from here actually. 2 and 1 you're comparing. 2 is not less than 1. Don't make sum as 0. Come here. 2 and 1. Yes, 2 is greater than or equal to 1. Now sum is equal to sum plus R2. What was there in R2? A first number. Okay. Take it and add it. And then again take subtract. Okay, here get subtracted. So compare and then again go for adding R3. So the process we repeat. Okay. Now similarly in the next case what happens? So this 3 goes to R0, this goes to R1, R2, R3. In this case this goes to R0, R1, R2, R3, R4. Now what we are doing, when the number of register extends, okay, so we are taking this. So up to 3 elements we do here. So when it crosses more than 3, so then we go for using the stack operations to perform it. Okay, here we're using the stack. So do we have another element? Load from the stack. Okay, so stack operations are used. So people understood?
Yes, sir.
Normally, so when you're passing, number of arguments which you're passing is more than the available registers. So now we can use R0 to R13. Okay, so 14 and 15 we cannot use. So R0 to R13 you can use. So if you want to pass more than 14 arguments, so then registers are not available. Then you have to go for performing the same operation using the stack. Okay. So this is let us stop here, and tomorrow we'll discuss with this example one more time, and then we will go to the next thing. Okay. So let us stop here. I hope people understood. So now here you learned how to make your C program and assembly program communicate. So calling the function from the assembly code which is written inside the C program, and similarly you understood how to call the C library calls inside the assembly code. Okay. So now we'll take attendance. Any doubts?
No, sir.